I'm Frank. It's nice to see a lot of people I know. And a lot of you I don't know. I was one of the first faculty members at Vector back when I was at University of Toronto. I recently moved to Dalhousie, where I'm leading a lab on machine learning in healthcare generally, but I kind of started with natural language processing back when I was an undergrad. And I like to say that I liked natural language processing before it was cool, but a lot of things have changed. Actually, that's kind of the subject of this presentation. So I prepared slides on some of our research. I was going to basically talk about one of our papers, but I switched up and I decided that I was going to basically be this old man yelling at the cloud for the next 20 or so minutes. Mostly because there's certain trends, like big picture trends that I've noticed, that have changed since I was an undergrad to now in natural language processing. Most of them, the vast majority of them amazing, but some of them not so amazing. And I kind of wanted to just touch on some of those today. And also there was a really good paper at ACL last summer that I just happened to randomly, accidentally see. And I'm going to try to spend more time on that paper today also, because I think it covers a lot of these same topics. Yeah, so back when I was a student at U of T, I had a debate with one of my committee members, like one of my professors, about whether computer science was really a science. And this professor said, like, no, definitely not. And he said something which is almost verbatim. This is like years ago, way too many years that I like to admit, but he said basically verbatim, any discipline that needs to use the word science in the title is not doing science. And I thought that was kind of cute, but my response is like, yeah, but like technically all sciences have the word science in them technically. So like physics technically is called the physical sciences, and no one would suggest that physics is not a real science. And it kind of sounded, this guy, I'm not going to say which one it is, but he likes to kind of badmouth other disciplines like social science and I think computer science at once. So it sounded like he was trying to be funny. I was young at the time and idealistic, and I said, no, computer science, we're definitely scientists. And this is also kind of verbatim. I said, computer science consists of scientists because, most of what we do is carefully gathering data and observations. We carefully choose models and we build these quantitative objective models on those observations. And then most of the papers we write are focused on our methods and the empirical processes. So how do we evaluate these models? It's all science from the top to bottom. It's just that we're studying artificial phenomena instead of natural phenomena. But some time has passed, and you occasionally see evidence of that maybe we're not entirely doing science. Maybe I was wrong. So I think a lot of you have these kinds of concerns also, right? So how reproducible are the models and the code that are part of the papers that we really like? Sometimes the data aren't available at all, or the data were briefly available and now they're no longer available. Some models are proprietary, so you just can't even open them up and play with them. Sometimes, especially these new models that we care to use in our projects, there's no papers writing about how they work at all. So you have to rely on somebody at the company who kind of gives you hints as to how these models supposedly work. And sometimes you're just not able to rerun the experiments, even if you had the code, right? It's very hard to train these large language models from scratch. But also beyond that, beyond the practical aspects of the scientific method, is whether or not the projects are framed in the scientific way in the first place. That is to say, are they falsifiable? So I'll talk about that in a second too. So generally, I'm going to kind of play the devil's advocate a little bit, but I want to emphasize that generally I'm extremely pleased by all this amazing stuff that's happening now. And there are some good trends, not just in terms of the abilities of these language models, but also just in terms of the scientific process. So code is much more available than it was 5 or 10 years ago when I was a student. Sometimes it's required. Sometimes, like if you don't submit your code, that's like a big red mark against you when you're trying to submit that paper. There's also concerns about overfitting or the lack of generalizability, and a lot of the new metrics involve like a suite of very different kinds of tasks. So a model that works on one should also work on the others, and so on. That being said, there's also obviously some bad trends. So, I think probably most of you who work with code have the experience of like finding a paper, there's a link to their GitHub, you get it, and you look at the code and it's very precise, and they even give you like the random seed that they use and the data and everything is pretty much taken care of. But when you run the code, it just doesn't work. Like you get results that are far off from what is reported. Like I said, increasingly the models are opaque, like you couldn't tweak them or understand them even if you could, because you don't have access to them. And again, like even at Vector, there was some initiatives to try to train large language models from scratch on large amounts of data. But even for institutes as well-funded and well-resourced as Vector, this is a big concern, to say nothing of other institutes. And then there's kind of the problems that I kind of see as maybe being problems, mostly again, just about the null hypothesis in science, right? So this is a little bit of soapboxing, but like we almost never see in computer science papers a null hypothesis saying, I'm trying to prove A, so I'm going to set up an experiment to prove not A first, and if that doesn't work, then the null hypothesis will be discarded. Usually, you get something that masquerades as a null hypothesis. So someone says, like, my system will be a benchmark that I specify on data that I specify against baselines that I specify. And whether or not it passes that, it sort of passes for the null hypothesis, but it's not really it. And even if all the problems mentioned on the previous slide with regards to reproducibility weren't the case, even if you could completely reproduce the work of others, reproducible models and code is not the same thing as having falsifiable claims in the first place. If you're doing science, but also if you're one of the increasingly numerous companies who are working with large language models, if you can't understand and you can't control and reproduce the models, then you're not doing science on one hand, but also you're going to have a hard time as a company. This might not be even relevant, right? So like the whole question of whether or not computer scientists are actually scientists or not might not be really relevant, because a lot of what we're doing is not technically science, it's more about innovation. Right, coming up, extending on the shoulders of people who came before you and refining things, being creative and coming up with new ideas and solving new tasks. So the point isn't science, the point is innovation. So quickly, I'm going to walk through sort of the history of speech recognition, which is also a big part of natural language processing, and just kind of touch on how the evolution of speech recognition itself touched on science. So one thing that is clear in the papers I'm going to show is that a lot of the big improvements in speech recognition were obtained by sort of operating in a sort of non-scientific way, okay? Again, I'm kind of playing the devil's advocate here, so it's a little bit glib. Generally, the process is about like ignoring more of the linguistic or the phenomena of language itself and trying to strip that away from our models. We have an awful lot of presupposing that full end-to-end speech recognition must be performant, even as you'll see, that initially was very rarely the case. And then also when we do have models that seem to improve over some other baseline, how we determine that that improvement has been made is also a little bit sloppy, in my opinion. So to start talking about sort of the difference between the models of speech recognition and the phenomena of natural speech. And I want to mention this quote. This is a quote, a very old quote from Jelinek. He said, "Every time I fire a linguist, the performance of the speech recognizer goes up." And this is way before the advent of end-to-end deep neural networks. So this is a old hidden Markov model. I'm not going to get into it too much, but just touching on a few things. It was based primarily on knowledge of language, right? So linguists broke down language into small chunks called phonemes, which you can see. Well, this is a big delay here. But as you can see down along this, this edge of the HMM, we have these small units called phonemes. How we tied these HMMs together also was based on some linguistic knowledge. So information from the different nasal phonemes like M's and N's were tied together so you could facilitate training. And this worked kind of, so this was sort of the preeminent model of speech recognition from like the 1980s all the way to around 2010. Which is a point where the first sort of split from this model came with connectionist temporal classification, or CTC, where the idea was we can get rid of the middleman. We don't care about phonemes. I don't care about physical articulation of speech. I have a spectrogram, like audio inputs, and I have characters or words I'm trying to predict. So just try to predict one given the other and just skip over the messy stuff in the middle. Okay, so in those days, in the early days of like 2012, they used simple RNNs. And they use a different CTC loss in order to tie everything up. I'm not going to go into detail there. So back in 2014, when this model was first produced, it did not beat the baseline. So from this paper, you can see this is the HMM, whose outputs are these little neural networks. And lower is better here. So these are error rates. And this model that they were pushing, this RNN with a CTC training objective, was getting around 13% errors when the old-fashioned HMMs were getting about 9.4% errors. So the baseline was still better. HMMs were still doing better on this task. than neural networks were. I want to point out also that it's great that this was even published, because technically this is a negative result. You failed to pass over a baseline. That's usually the death knell for a paper at a conference, but this was published because it introduced a really interesting new idea, CTC. A little bit later, other new advances in neural networks were brought in. So this is 2015. So this is the original listen, attend, and spell project. They had like a pyramidal by LSTM that encoded the audio, and then there was like an attention-based layer of LSTMs on the top that decoded it. So this kind of was a first introduction of the attention mechanism into speech. It could do cool new things. So now, again, it was skipping over phonemes and all of that linguistic knowledge. It could do cool new things like, from the spectrogram, this colorful thing at the top, it could figure out, where the characters of the output text are according to the attention. This is basically the attention mechanism from the decoder. So that was something we couldn't do with the HMMs very easily. This also failed to beat the baseline. So here again is HMMs, much lower word error rates than, a listen, attend, and spell, even with resampling added, even with language model rescoring, even with a lot of tweaks to this neural-based approach, HMMs were still the best. And then around that time, a bit later in 2017, some people who don't work in language said, well, these spectrograms look like images. They're kind of like big, colorful fingerprints. We should use CNNs on the raw spectrograms, and then maybe that will somehow get us end-to-end neural-based speech recognition. So this is Yoshua Bengio's group. They have 9 convolution layers without pooling, some fully connected layers on top. So you basically scan over the spectrogram, and that's going to give you your word outputs. So finally, after a few years, we finally beat the baseline. The baseline, they did not include HMMs, so maybe this could never beat HMMs. So the baselines were all other neural units. But as they showed here, they went from 18.3% phoneme error rate to 18.2, so a 0.1% improvement using these CNNs, which was seen as a great thing because this was a very popular paper. Many more years passed, and these baselines were still very hard to beat in speech recognition. But finally, a model that I greatly admire, Wave2Vec2 came out. So Wave2Vec2 is self-supervised. It learns sort of representations internally, explicit ones. So there's, again, kind of stacks of CNNs that spit out representations, encoding representations. These used to be, so then you quantize them. So you can cluster them together. The precursor to Wave2Vec2 used k-means clustering for what it's worth to get the units. So it's not saying this is a p sound and this is an a sound. They're sort of these soft units, but they're units nonetheless. So we encode the speech again with CNNs. We pass those into a masked transformer. And then this is how we're going to do speech recognition going forward. Okay, they did a lot of work on this. There's a ton of innovations in it. So there's kind of 2-part losses. There's a contrastive loss, which compares, the appearance of the input according to a lot of those different hidden units. So if it's this phone, I'm saying phoneme, if it's this imaginary phoneme or that imaginary phoneme, how different are these things? So you can learn differences between these internal representations using a contrastive loss. There's a diversity loss. I'm not going to go into the details here either, but they did a lot of work. They did a lot of fine tuning, spent a lot of time trying to make this neural-based model work as well as possible. And then finally, the moment we've been waiting for over the course of like 10 years. Now down here at the bottom, we have our old-fashioned HMMs, which on this data set, we're achieving something on the order of 5.8% error. And now, with a massive model, with all of those tweaks, we get down to 2% error, right? Which is a huge improvement. Finally, this is a reasonable looking baseline. Some questions come up, like why aren't HMMs also included in these other comparisons when you're looking at different amounts of training data? They also don't really put any effort into the HMMs. They just take it off the shelf and run it. Maybe if they also introduce a contrastive loss and a diversity loss into the HMM training, they would have improved this 5.8 down a little bit also. But also then it's just a matter of practice, right? So in practice, like in a table, 5.8 certainly looks a lot bigger than 2.0, but how does this actually translate into real world usage? Those are all questions for outside of this paper. And then finally, just to wrap up this section, here's another paper that sort of, in speech recognition, these differences are very small, right? Like I talked about when that CNN-based approach to speech recognition was introduced, the improvement was literally 0.1% over like one of the baselines that they were providing. So in this case, I just want to highlight this one. So this is also a paper I like a lot. This is relatively old. It's from 2012. Again, HMMs were the baseline, and they achieved 22.7% phoneme error rate on this test set called Timid Core Test. And their end-to-end deep neural network model achieved 20.7%. And this was a very popular paper at the time also. It's like, you can do speech recognition with neural networks too. So the question is, though, is 2% meaningful, right? So this, I think, I want to mention this just because it comes up a lot in our work where, you know, we beat the baseline by on the order of 2%, and then we pat ourselves on the back for that. But if you think about it a little bit, like, is it actually meaningful, okay? So I'm not suggesting this is the right way to approach power analysis, but a standard way to do power analysis is to use like a Cohen's d as an effect size measurement. You set alpha to be something like 0.01, which is pretty permissive. You can do 2 tails, 1 tail. You can set power to 0.8, which is also very permissive. And then power analysis tells you how many samples you would need in order to say whether 2% was a significant difference. This is more than just random statistical sampling that caused this difference. But this particular training set, TIMIT, core test, only has 192 sentences in it, right? So this is an ancient base benchmark, which fits on a CD. Many of you probably don't even remember CDs, but it's one small test set on something that literally fits on very archaic technology. So again, devil's advocate, I would love all this work, but if we're going to make claims about whether one system is better than another system, we have to be skeptical. And you know, and there's tons of problems with statistical testing. Like this power analysis assumes Gaussian distribution, which is not always the case. But anyways, I wanted to highlight that. So the takeaway from this little first 10 years of effort is that if you really believe that eventually these end-to-end neural models will beat, you know, baseline that is decades old, eventually you will accomplish that. But we have to remember sometimes that like the amount of these differences, like these 0.1% differences, might not actually be very meaningful. And part of the reason is that I think many of us sometimes are guilty of this also. We have the model that we invented, and we kind of wanted subconsciously to win against the benchmarks. So we'll run some experiments. They won't give us the numbers we expect. So we'll go back to the drawing board. We'll provide some tweaks. We'll change the data a little bit, change the hyperparameters, but usually towards the goal of, you know, making sure that our model beats the others, which is something that happened a lot in those papers I highlighted. It happens in many of our papers. But that brings me to kind of the main thing I wanted to talk about, which was this paper I saw last year at ACL. Okay. And the idea generally is that, you know, we want some kind of aim, and we kind of take shortcuts in order to achieve that aim. So this is the paper. It was written by people from Bloomberg and Cohere and Oxford and DeepMind. And the theme of it is the idea of scientific debt. Okay. So scientific debt comes from the idea of technical debt, and technical debt is something they have in software engineering teams, where you kind of rush to have a solution. But if you rush to have a solution, like if we're in a bottom-up sort of spiral-based approach to software engineering, you end up cutting too many corners, and things end up breaking. And you kind of should have put more planning into the approach from the beginning, right? If you rush too fast, you'll pay for it later. So in this paper, they talk about the sources of scientific debt in natural language processing. The first one involves hyperparameters and other experimental settings. So there's lots of papers that just focus on the slight variances in hyperparameters can result in very huge differences in the performance of the models they're evaluating. They also touch on the proprietary and opaque nature of many pre-trained language models and their training data sets, especially the very large ones. They also touched, like I did a moment ago, on problems of computational costs. You know, it's very hard to actually do the kind of work we'd love to be able to do. Even if we wanted to do like cross-fold validation and everything with these large language models, it's way too costly to be able to do so. So even if we wanted to do the right thing, it would be very hard to. And then, of course, there's the incentive in our discipline, right? So in our discipline, the incentive is to publish. In order to publish, you have to get the best results. You know, I don't think it's controversial to suggest that I think sometimes people might maybe just subconsciously not pick up on some errors they're making. What are the consequences of taking these shortcuts? The one they focus on particularly is the fact that a lot of papers, we're changing many things at once, okay? I'll give you an example of that in a second, but the problem with this is if you're changing hyperparameters, the data, the architecture, the task, then if a reader is going to read your paper, they're going to have a difficult time figuring out, well, what of all these things that have changed, what is the aspect that actually contributed to the model behavior. Like, will I be able to get this kind of behavior if I just use transformers also, or do I need the same data, et cetera, et cetera? It's also still hard to distill generalizable patterns. So how well would a model work in practice if I were to transfer it to new tasks, new settings, maybe at low resource scenarios? And then the main theme of this paper also, it's very hard to replicate things and to assign credit. This is actually very similar to point one, but is my model good because I use a transformer, or is it good because I use a lot of things in concert? And then they make the point in this paper that if we're not very careful, we can flock like lemmings or pigeons or something else along to whatever the trend is, catch on to the most popular paper of the year or the month, and just use that model instead of maybe thinking about others, which can, I'm not too worried about this, but they suggest, the paths can be misjudged, and therefore we can waste time using models that aren't necessarily optimal. So that brings me to BERT. Okay, so for a brief period, the field of NLP was sort of tongue-in-cheek called BERTology, because everybody was doing BERT-based models. So they focus on BERT. So when BERT came out a long time ago, it outperformed the baselines. Again, they chose the baselines, and then it outperformed ELMO and GPT-1 by substantial margins. Okay, and I like this paper, but when you read it, it's sort of like reading an Apple press release. It's like we have this feature and that feature and this feature and all these cool things that you want. And that's what these next bullet points suggest, right? They use a lot more data to train these models than GPT or ELMO had at their disposal. So they're bigger, and then also they had more varied types of data they use for training. They used whole model fine-tuning on every downstream task. So ELMO, for those who remember, you'd train it, you'd pre-train it, and then you'd kind of freeze the word embeddings, and then you do some training afterwards on the task, but the word embeddings would be frozen. They use transformers. So GPT obviously used transformers, but ELMO used these BioSTMs. And then they also introduced probably the most novel contribution was this bidirectional masked LM loss, which obviously GPT-1 and ELMO did not have. And then there's other factors too. So the more data, but so the models were a lot bigger. They trained BERT for a lot longer than ELMO and GPT-1 had been trained on. They introduced this novel tokenizer, which is also a really cool feature that we all should use today, but it was also another new advance that differed from the others. So the point of this paper was, just as sort of a proof of concept, try to isolate BERT's, like mostly the bidirectional masked LM objectives, so the most novel aspect of this work, to isolate it by redoing the experiments with ELMO and GPT-1, but making the experimental conditions as similar as possible. So they used the original BERT pre-training data, Wikipedia and book corpus, so they gave that to GPT-1 and ELMO. They used BERT's word piece tokenization, so the token pre-processing was common across all the models. They fine-tuned the whole model, so they didn't just freeze the embedding. It goes into a lot of detail about this part. So like they had to swap out the BioSTM aspect of ELMO with transformers that nevertheless still only looked, because ELMO has LSTMs working in two directions at once. So they had to have transformers that only kind of looked either forwards or backwards in time. So they go into some detail on how they did that, but I think they did a reasonable effort into matching like what ELMO was trying to do with using transformers. And then the hyperparameters for all these different architectures obviously are going to be different, but they put an equal amount of effort into optimizing those across all of the models. So here are the results of BERT when it was originally published. So these are the old blue tasks along the top, and in this case now higher is better. And as you might remember, like BERT, clearly cleaned the clocks of ELMO and GPT-1 across all of these tasks. So this is like the big confirmation or validation they needed. But in the paper that I'm talking about, the scientific debt paper, they redid everything. So there's two things to notice here. First of all, so they reran BERT from scratch also, and the results were a little bit lower sometimes they're a little bit higher. Sometimes they're exactly the same. But the point is, like, there's no like single number that represents, BERT must get 52.1 on COLA because, if you try running it again, it might just get 50.8. But then the important stuff is more down here. So if you make the playing field level and you give ELMO all of the benefits that you gave BERT, same training data, same pre-processing, same effort in hyperparameter optimization, you don't necessarily beat BERT, but you get a lot closer, right? So I'm not going to go through all these details, but the comparable Elmo variant run gets a 46.8, whereas before it only got a 36.0. Okay. Sometimes it's extremely close, and I think sometimes it even beats the BERT. So at the very least, Elmo and BERT might not be so different after all if you compare them fairly, but sometimes Elmo might even come out ahead. So they conclude the paper by saying that what we need to do as a community is to establish more standard publicly available pre-training corpora and at multiple scales. And I think to a large extent, this is already happening. A lot of new papers from the past 6 to 12 months are producing lots of new data sets. It's important to delineate where the differences are. So like also ablation studies are something that's becoming more popular in NLP, which is great. But in order to really understand, if you're changing many things at once, what is the contribution of these different contributions to the eventual performance? Yeah, putting a reasonable amount of effort, like even if you have your favorite horse in the race, you have to still try to give yourselves difficult baselines to beat. And they also talk about doing more extensive ablation studies. This is not always possible, of course. Like it's really hard to do an ablation study with an opaque API-based model. It's not impossible, obviously, but the things you're ablating aren't necessarily the internals of the model, and so on. And there's a lot of other good work in this area. So our own Colin Raffel has done some work in how to do ablation studies with large language models. So just to wrap up. I had a lot more to say, but I have not much time now anyway. But so on one hand, like again, I mentioned at the beginning that I got into NLP before it was cool, like when I just got into it because it was an interesting idea. And since then to now, so many things have changed. And the main thing is we can now do tasks that were previously kind of unthinkable, right? Like speech recognition when I was a student was something that could barely understand the difference between yes and no on your phone. And now, of course, it's much more performant. And in many cases, obviously, NLP is fulfilling the promise of previous generations of AI. However, like we have to balance things out. Many of you end up working with organizations that are not necessarily academic, that are companies that are using large language models or want to incorporate large language models into their business. And it's important just to remember some of the challenges that exist with these models. Primarily in the fact that it's really hard to reproduce these models. So like GPT might have one model in February and another model will be running in March, and you don't necessarily know what changed. They don't really publish those details at all. So it's really hard to reproduce results. And if we can't reproduce results of others, then that definitely comes down on the side of we're not doing science, to that old debate. Like that paper, the scientific debt paper from ACL last year, it's really hard to explain any improvements that are coming in. And as always, like, I'm not suggesting everyone starts doing statistical testing, but, we have to just basically be aware of when we're trying to confirm that one system supposedly works better than another. We have to be skeptical is the point. I wanted to highlight this thing here. This is also, most of this is, again, I'm playing the devil's advocate for a lot of this talk, but it's been said by others, that we're kind of NLP is turning into glorified quality assurance for OpenAI. So imagine, if 5 years ago, we had papers like, in ACL saying, this is how you can get really good search results from Google. It's not too different than, what we might be seeing these days with GPT in some extent. That's it. Thanks so much for listening.